Now in the last video I said that it's very convenient to have a unit that is similar in size to whatever you're working with. Now in chemistry we're working with just absolutely unimaginable numbers of molecules and atoms. So it'd be nice to have a unit that is going to hide those large numbers. So there's a fifth SI unit that we're going to define here. It's the mole. 1 mole is Avogadro's number things, whatever the units of the stuff you're working with. Say you were working with elephants. A mole of elephants would be 6.022 times 10 to the 23rd elephants. So this could be anything. Usually in chemistry, the things that we're talking about or interested in are molecules. Now, it's a counting unit then, like a dozen. You can say 1 dozen is 12 things. So a dozen eggs is going to be 12 eggs. A dozen elephants will be 12 elephants. It doesn't matter what the units of those things are, what the things are. You're counting them with a dozen. And the mole is exactly the same way. That is the concept here. So if I had a mole of eggs, that would be 6.022 times 10 to the 23rd eggs. Whatever your units are, whatever your things are, whatever your small entities are that make up your sample. Now, we can use this as a conversion factor, this definition of moles. Let's put a box around that because that is something you should remember. Suppose I have a million molecules. Let's put it in scientific notation so we can show how many significant figures we've got here. We've got 3. A million molecules. And I want to figure out, it could be molecules of anything. It could be molecules of water, molecules of ammonia, molecules of O2. It's going to work exactly the same way no matter what, because it doesn't matter what your things are here. If I've got a million molecules, and I want to know how many moles is that. So this is my target. This is really just a unit conversion problem, like we have been doing all along. And this is just a relationship that you can use in unit conversion problems. Down here I'm going to write this relationship like this. Well, 1 mole is 6.022 times 10 to the 23rd molecules. That is the relationship that links molecules and moles. Okay, now let's actually do the calculation. I have to turn that into a conversion factor here. Alright, I need to put molecules on the bottom. And I need to put on the other side moles. There's a 1 always sitting in front of the moles. And the 6.022 times 10 to the 23rd always goes in front of the molecule. So don't put that number in the wrong place, right? There's always a 1 in front of the moles here in the definition. Okay, well, I can do the math then. I can see that molecules is going to cancel out and I'll be left with moles. How do I enter this into my calculator? I'm going to have to use scientific notation, E-notation. It'll be 1.00 EE6 divided by 6.022 EE23. And I'm going to get the right answer if I press equals. It's going to be 1.66 times 10 to the minus 18 moles. Okay, So I've converted molecules into moles using this as a conversion factor. Now let me show you something that can go wrong when you're not using E notation that we learned about in another lesson. Suppose you've got the same problem and you key it in like this. Let's key it in like that and see what happens. It looks the same, right? This looks right. But if you don't use E notation, the way I just did to get the right answer, you're going to get something you don't expect. Okay, so I'm going to type it in just like this. 1.00 times 10 to the 6 would be 10 to the 6th power divided by 6.022 times 10 to the 23rd power. I got a completely different number. Look what I got. Ten to the 28. What went wrong? Well, the calculator interprets what you just typed in this way as 1.00 times 10 to the 6th divided by 6.022 times 10 to the 23rd. Do you see the difference between what's here and what's here? This is a very common mistake that students will make, and it all comes from not using the E notation. Now if you use E notation, if you say divided by 6.022 E23, it will keep this whole thing down in the denominator. But if you split it up like this, it's only going to divide the first thing and then multiply the second thing. That's what you're telling it to do. So that's the wrong way to do it. The moral of that story is use E notation when you're doing these kind of problems. Now, let's do one more. Let's go the other way. Let's suppose instead of knowing molecules and wanting moles, I know moles and I want molecules. So suppose I have 3.71 moles of water, and I want to know how many molecules of water that is. Okay, well I can use the fact that 1 mole of water is 6.022 times 10 to the 23rd molecules, 23rd molecules of water. And there's my roadmap. So turn it into a problem. 3.71 moles. Now moles has to go on the bottom. And then molecules is going to end up on top. So basically I'm going to have 3.71 times 6.02 times 10 to the 23rd. Key it in. 3.71 times 6.022 E 23. I'm going to write molecules down because the moles have canceled out. I have 3 significant figures here, and I've got 4 significant figures here. So I'm going to end up with 3 significant figures here.